In this video, we're going to talk about how to use a series solution to solve a differential equation. In particular, I have a famous equation called the Airy's equation, y double prime minus xy is equal to 0. And what we're going to work through in this example is how to use a series solution to find the answer. Now, I'm going to begin by assuming that I have a series solution. That is, I'm going to assume that the y looks like an infinite sum, I'll put an indexing variable of n equal to 0 up to infinity, of some coefficient Cn and then powers of n. So this is in fact a power series centered around 0. Now, if you had checked out the previous video on this series where we talked about when can we expect solutions of this form, you'll note that the coefficients of y prime, which is 0, and the coefficients of y, which are just x. So these coefficient functions are either 0 or just x. So both of them are what we had described as being analytic. There was no problems, for instance, of a division by 0. And so every single point is a so-called ordinary point, which means that we can expect solutions that look like this. Nevertheless, I'm going to assume that I have this. And I'm going to have to take two derivatives. So let me come along and compute that and figure out what y double prime is going to be. And here I'm going to do term by term differentiation twice. So that means I just leave the sum out the front here. Then the constant Cn has remained, but I take two derivatives of the function x to the n. That gives me an n and an n minus 1 and then an x to the n minus 2. Okay, so taking the y and the y double prime, plugging both of those into the differential equation, that's going to leave me with, well, for y double prime, I'm just going to copy and paste n equal to 0 to infinity, the Cn, the n minus 1, and the x to the n minus 2, so nothing new. But then I need to subtract off x times y. So what I'm going to do is put in the y, but I need to add one more x. So here's how this works. I'll take the sum from n equal to 0 up to infinity of Cn, and then it should be x to the n, except for the fact that there's one more x. And that's what I actually write is x to the n plus 1. So that's representing the single x that I have out the front, as well as the n that I have here, that together comes and gives me the n plus 1. This equation then on the right-hand side is, of course, just equal to 0. Nothing to do there. So now I want to analyze this, and I really want to try to compare like terms, but the problem is that on this left expression, I have an x to the n minus 2, and on the right, I have an x to the n plus 1. They look very different. So the approach that I'm going to do is shift indexes. And I can do this for either sum, but I'm actually going to shift it on the first sum and make both of them look like x to the n plus 1s. So what I'm going to really focus in is on the first of them. I'm going to take the n in the first and send it to n plus 3. The reason I like that is that x to the n minus 2, when you add the 3, is going to become x to the n plus 1, and so they're going to align. Okay, so giving myself some space, this is going to become the sum, well, n plus 3 equal to 0 is the same thing as n equal to minus 3, and we're going to come and tweak that in a moment. See n plus 3 times n plus 3, n plus 2 now, and then finally x to the n plus 1. And then I actually have a negative of sum, but I may as well just move the sum to the other side because it's equal to 0, and so I'll take this as the sum from n equal to 0 up to infinity of, well, nothing has changed here, so I'm just copying and pasting. So now I have it written that they are both coefficients of x to the n plus 1. There's a nice alignment. I can clean up this n equal to minus 3 a little bit just by noticing that if I plugged in n equal to minus 3, it would give a 0. And if I plugged in n equal to minus 2, that would equal to 0. So instead, I'll just start this at n equal to minus 1 since the first two terms don't do anything. Then I'm going to note that even with that adjustment we just made, the left sum starts at minus 1 and the right sum starts at 0. So there's an extra term in the left sum. So I'm just going to pull that extra term out so that the two sums start in exactly the same way. That is, I'm going to say that this is the same thing as, okay, if n is equal to minus 1, then Cn plus 3 is going to be effectively C2. I then have a multiplication by 2, a multiplication by 1, which I won't write down, and then an x to the minus 1 plus 1 is just 0, so an x to the 0th term, and I'll just leave that there. Then I add to that the sum now starting at n equal to 0 since I've pulled out the minus 1th term, and I copy everything else. There's an immediate consequence of doing that. If I was to come along and plug in x equal to 0 in for the two different places, thinking this power series is just some function of x, so I can plug in x equal to 0, then what you would have would be 0 on the right-hand side is equal to, well, this c2 times 2, x to the 0 is just 1. So in other words, you'd be like c2 is equal to 0, and so that immediately tells us that the c2 has to be equal to 0. So we can pull out that first term, and now we get to ignore it. So then what I'm going to look at is the coefficient of x to the n plus 1 over there and the coefficient of x to the n plus 1 over there. Those two things are the same. And thus we get the recurrence relation that Cn plus 3 times n plus 3 times n plus 2 is just equal to Cn. Okay, so let me give myself some space and pull that up to the top because this is the recurrence relation that we want to study. Okay, so let's just try writing down a bunch of terms for this thing. The first thing I need to plug in was n equal to 0, and so I have some C0, and I'm not going to say anything further about that because I have no relationship that I can use. It just is a constant. Now, what this relationship does is if you know some Cn, it tells you the value 3 beyond that. It tells you Cn plus 3. So I have no way of specifying the first C0, and I also have no way of specifying the first C1. That's also just going to be some constant. And then C2, as we decided earlier, was going to be equal to 0. We've done that separate analysis. But now we can start making something new when it gets to the value of C3. Because, well, what is C3? C3 is 3 more than C0 in its index. And so I can plug this in. This is going to be equal to C0 divided by 3 and divided by 2. So I'm taking the n plus 3 and the n plus 2 with n equal to 0 and dividing them out. Okay, so that was nice. Well, let's see about C4. 4 is 3 bigger than 1. So it relates to C1, but now is divided by 4 times 3 when you plug that into the formula. So in other words, there is this relationship between C0 and C1, and there's another relationship between C1 and C4. Okay, let's keep on going. What about C5? Well, C5 is related to C2, and C2 is 0, so C5 is going to be equal to 0, so I have a relationship there. All right, let's just do a couple more just to get the pattern really locked in. So C6 is then related to C3. So let me write down the C3. It was C0 divided by 2 times 3. I'll write it in that order. And then if I have n equal to 3, n plus 3 is 6, and n plus 2 is 5. And so I'm going to have I skip 4 here, and then I have 5 times 6. It's kind of weird. Right, so the C3 then became related to the C6. Okay, what about C7 then? Well, this is the same thing as the C4, but divided by 7 times 6. So it's C1 divided by the 3 times 4. I skip 5, and then it is a 6 times 7. C8 is related to C5, which was 0, and so forth. Okay, so we have this sort of long pattern here that we're seeing. We could keep on doing this as long as we wish, but can we come up with a general pattern? So I think we can say the following. If I want to talk about C3n, so this is 0, 3, 6, 9, and so forth, all of those are the ones that are related to the C0. So the general pattern here is that it is going to be the C0, then divided out by, well, what did it look like? A 2 times 3. Then you skip 4. A 5 times 6. And then you'd skip 7. And then it would be 8 times 9. And then you skip 10. And then it would be 11 times 12. And generally, this goes on in this matter until you multiply by a 3n minus 1 times a 3n. So for example, if it was C9, which would be n equal to 3, the last thing you would multiply by would be 1/8 and then 1/9. All right. Then if I want to do C3n plus 1, so that's the 1, 4, 7, and so forth, this was all related to the C1. But here it started at a different index, so it was 3 times 4, it missed 5. It was 6 times 7, it missed 8. It'd be 9 times 10, and so forth. Generally, it would end up at 3n and 3n plus 1. So those are my generic coefficients. Finally, if it's C of 3n plus 2 here, so now I'm imagining 2, 5, 8, all of those ones are going to be 0, so those ones at least go away to 0. Alright, so let's try to write down our final answer. It's going to be a bit of a mess, but it simplifies really as just the sum of two different things. There's a bunch of terms that are related to the C0 and a bunch of terms related to the C1. And so the way I'm going to write it is I'll put the C0 terms out the front, and the C0 corresponds to all of the n being 3 times something. So, for example, the very first term is just the C0 times x to the 0 by itself. Maybe I'll write it as times x to the 0. And then we were going to have an x cubed term, and this one was going to be divided by 2 times 3. And then there'd be an x to the 6th term. This would be the 2 times 3 times 5 times 6. And in general, an x to the 3n over this long expression we had described that ends in 3n minus 1 times 3n. So that long thing is my portion that's all multiplied by the C0. I would then have a similar expression that was the C1 terms. It would be a whole long mess there as well. Powers like x to the 1, x to the 4th, x to the 7, and so forth. So the very first term is just x to the 1. Then there's going to be that x to the 4th term divided by 3 times 4. There's going to be an x to the 7th term divided by 3 times 4 times, you skip 5, and then 6 times 7. And then you have the generic 3nth plus 1th term, which I'll write as the normal beginning as you would expect, and then 3n plus 1, and then plus dot dot dot. I messed the plus dot 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 on the first one. So this is quite a messy expression. As we had seen in an earlier video when we did the same thing and our solution was e to the x, the recurrence relation was so nice and easy that you could just sort of put all of this mess and call it n factorial. But here it's not quite a factorial, and that's just sometimes the best you can do. You try to write out what the general term looks like this. And in practice, if you had to write out, say, the first 5 terms or 10 terms or even 100 terms, then you could do that relatively straightforwardly. So 2 things that I want to note. All of these messes can be thought of as a y1 and a y2, in which case your expression is much simpler. It's a c1 y1 and a c2 y2. Indeed, for a second order differential equation like this, our theory gave us that we should expect 2 different series solutions and that there would be a c1 y1 and a c2 y2. So we've got exactly what the theory told us. And then finally, there's a question of convergence of these expressions. So then you could use the ratio test, and indeed I'll leave that as an exercise for you to do, to deduce that yes, these series are convergent actually for all values of x. So nevertheless, this is our methodology for how to solve a differential equation using series, at least when all of our points are so-called ordinary points.